Okay, so as we look at these, we're just solving for x just like normal. So for number 1, you should have distributed on the right-hand side and gotten 3x plus 1 equals 2x minus 8. If you subtract 2x from both sides, you just get x. And if you subtract 1 from both sides, you get negative 9. So x equals negative 9. That equation has one solution, negative 9. Number 2, you are also distributing, and you get 3x plus 1 equals 3x minus 12. Now think to yourself, does that make sense? Can 3x plus 1 equal 3x minus 12? No, okay? And algebraically, let's look at this. If we subtract 3x from both sides because we want to combine like terms, essentially, we see that the 3x's cancel on both sides. And we have 1 equals negative 12. Well, that is not true. So what has happened is that all of the variables have canceled, and we have a false statement. So what does that tell us? Our answer is no solution, right? So if all of your variables cancel and you get a false statement, there's no solution. But if you look at number 3, 3x minus 6 equals, distribute, 3x minus 6, it makes sense that no matter what you plug in, it's going to work because it's the same exact thing on both sides. 3x minus 6 equals 3x minus 6. But let's look at it algebraically here. If we subtract 3x from both sides, again, we see that they cancel, but this time we have negative 6 equals negative 6. Variables cancel, but we have a true statement now. Negative 6 does equal negative 6. So what does that tell us? Yes, all real numbers are infinitely many solutions. Anything you plug in there will work. So when we were solving these equations, we had the option of having one solution, no solution, or infinitely many solutions. And that's what we're going to have today too when we solve a system of equations. So let's look at this next section here. It says solve each system algebraically. So that means substitution or elimination. Which method is number 1 set up for? Elimination, right? Because the variables are lined up and we almost have opposites, but not quite. We just need to change the sign. So it doesn't matter what equation you change the sign on. I'm just going to do the bottom one. So the positive 2x becomes negative 2x. The negative 3y becomes positive 3y. And the negative 4 becomes positive 4. Why did we do that? Because we want to solve by elimination, so we want to get one of the variables to eliminate, which means that the numbers in front have to be exact opposites. So now we have 2 and negative 2, which gives us 0, or they cancel. Negative 3 and positive 3, also 0. They cancel. So nothing is left on the left-hand side. All of the variables have canceled out. And on the right-hand side, we have 6 plus 4 is 10. So this should look very similar to that number 2 that we did above. All the variables are gone, and it makes a false statement. So what does that tell you about this system? No solution. That's good. There's no value of x and y that would make this system true. Okay, what method is number 2 set up for? Substitution, right? Because the y is already solved for. It's already by itself. So if we know that y is equal to 2x minus 4, we can circle that and plug it in for y in the other equation. So when we do that, we get 4x minus 2. Take out the y and put in parentheses 2x minus 4 equals 8. Distribute. and combine like terms to solve. So you have 4x minus 4x. Those are on the same side, so you just combine like terms. 4x minus 4x is 0x, or just 0. And you have 8 equals 8. So again, your variables have all canceled out, but this time you have a true statement. So that tells you that the answer is all real numbers or infinitely many solutions. Questions on that? On either one of those? Okay, number 3. What method is that set up for? Substitution. But before you begin, what's special about that second equation? There's no y. You could solve for x and know the value of x right away. So if we subtract 2 from both sides, you get x equals 0. Does that mean no solution? No, 0 is a number, right? You can have 0 apples, or you can have $0, or there could be 0 days left until break. 0 is a number, so that's okay. We're going to take that 0, we're going to plug it in for x, and we're going to solve for y. So if you subtract 3 from both sides, you get y equals negative 3. And written as a coordinate, it would look like that. Just kidding. Yeah, that's right. So when we solved the system of equations, we had 3 options. We had the option of no solution, infinitely many solutions, or exactly one solution. Okay, so let's think about this graphically. If I graphed a system of 2 equations, so if I graphed 2 equations and they had one solution, where do you find that solution? Where they intersect, right? If I take 2 lines and I graph them and they cross or intersect, that one point where they intersect is the one solution. Bless you. So what would it look like if there was no solution? They wouldn't intersect, right? What is it called when lines don't intersect? They are, that's right, parallel. And what do you know about the slopes of lines that are parallel? They're the same, but the y-intercepts are different. Okay, so let's look at number 4. It says solve each system by graphing. And somebody last hour said, well, wouldn't it be set up for elimination because the x's are already opposites? Yes, but they specifically said to solve by graphing, so you have to pay attention to that. Okay. You could graph using the intercepts, or I'm going to go ahead and put these into slope-intercept form, okay, because I want you to see how the slopes are going to be the same. So let's, for the first one, subtract x from both sides. And then we have to divide by negative 2. And we end up with y equals negative 1/2 x plus 4. That's in y equals mx plus b. So that means that your y-intercept, or where it crosses the y-axis, is 4. That's where our starting point is. And then we have a slope of negative 1/2. So we're going to go in the negative direction, down 1 and over 2. Rise over run. Oh, you know what? Stop. If I subtract x from both sides, that's negative, and the slope is positive. My mistake. We're going to go up 1 and over 2. Same y-intercept, different slope. And for the second one, we're going to add x to both sides. We're going to divide by positive 2. So we end up having a y-intercept of -3. So we plot -3, and that's our starting point. In the positive direction, we're going to plot our slope, which is rise over run, 1/2. So rise 1, run 2. So graphically, you can see that these lines do not intersect. So what does that mean? No solution. They are parallel. And if you look at them algebraically, so if you look at the slopes, the 1/2, you will see that the slopes are the same. The y-intercepts are just different. So it's shifted. Questions about that? So what do you guys think it would look like if there were infinitely many solutions? What would it look like graphically? It's going to have to be the same line, right? Because they're going to intersect at every single possible point. So for number 5, let's put that into slope-intercept form. Subtract x from both sides. And divide by 3. The y-intercept, or b, y equals mx plus b, is -3. That's our starting point. And from there, we're going to go in the negative direction, down 1/3, rise over run. We're going to do the same for the second line by adding 2x to both sides. We're going to divide by -6. And you will see that they are the exact same line. So yes, they have the same slope, but they also have the same y-intercept. So really, you don't even have to graph it again, but just for sake of color coding, I want to show you that it's the exact same line. So on your paper, if it has infinitely many solutions, there should only be one line because they are the same. Okay? So this is infinitely many solutions. They're the same line. Questions? Okay, so algebraically, you can have one solution if you get an x and a y. You can have no solution if all your variables cancel out and they make a false statement. Or you can have infinitely many solutions if all your variables cancel out and it makes a true statement. Graphically, if they intersect at one point, there's one solution. If they don't intersect, if they're parallel, then there's no solution. And if they intersect throughout the entire line, if it's the same line, then there are infinitely many solutions. Questions?